In this video, I will discuss what Richardson extrapolation is and how we can use it in order to come up with more accurate finite difference approximations of derivatives. Now, what is Richardson extrapolation? Well, the idea is to calculate or come up with a more accurate approximation of the derivative of f, or the second derivative of f for that matter, from two less accurate approximation schemes. And we'll see how that works in a minute. It was devised by Lewis Fry Richardson, one of the pioneers of computational science, in my opinion. In this movie, there's a nice explanation of how Lewis Fry Richardson kind of devised the first numerical computation of a weather forecast simulation. And it's quite an interesting figure. He was also a pacifist, but he really contributed a lot to numerical mathematics and computational science as a whole. Now back to Richardson extrapolation. The whole methodology is basically based on extrapolation of the asymptotic behavior of the truncation error with respect to the grid spacing. And we will use then two less accurate schemes calculated on two levels of grid refinement H to cancel out leading order truncation error terms. Now that's really quite a mouthful to say it like that, but once you see it in action, you will realize it's actually remarkably simple and allows us to come up with to easily come up with these higher order approximations of the derivatives. In addition to differentiation, numerical differentiation, it's also relevant for coming up with more accurate schemes for numerical integration, which is the topic of next video lecture, or also solving ordinary differential equations numerically, which is our final video lecture. But in this context today, we will discuss it for numerical differentiation only. Now let's just look at an example and really apply Richardson extrapolation, as this will allow you to see how it works. So recall, for example, this forward finite difference scheme for approximating the first derivative at xi. So the slope of this purple line, that's this first derivative, and what a simple forward finite difference scheme does is it takes the function values at xi plus 1, subtracts the function value at xi, and divides it by the spacing between xi plus 1 and xi. The truncation error that you end up with is of order h. And to kind of make it a bit more explicit, this truncation error somewhat looks like this. So we have as a leading order term here, this is minus h over 2 times the second derivative of f at xi minus h squared over 3 times the third derivative, etc. Or you could write this only as a second derivative by using this xi in between xi and xi plus 1. So we have our finite difference approximation, which is a function of h. We can vary h. H is a user-defined input parameter, let's say. And we have the truncation error, which is, well, the leading order term, which is expected to be the largest term. If h is small, h squared over 3 factorial is very small. So h over 2 is expected to be relatively large. So the leading order term here is proportional to h. So we say the truncation error is of order h as well. So we can rewrite this actually as the first derivative is our finite difference approximation plus an error of order h. Or we can expand a bit on this error and say, well, this is approximately something like a constant times h. So we say that this second derivative of f at xi, that's a number, it's a constant, divided by 2. So this is a constant times h plus something of order h squared. And this h squared comes from here. So now we just have expanded this order h a bit more explicitly into a constant times h plus something smaller of order h squared. The idea that we now have is to try to compute this d at two levels, namely h and 2 times h, because they should both approximate the same value of the derivative here on the left-hand side. And in doing so, well, we try to combine those two formulas to cancel out this leading order error term. So we want to cancel out this term actually somehow by using d evaluated at two levels, h and 2h. We want to cancel out this term, and then the remaining error will be of order h squared. So we want to come up with a second order scheme from our first order schemes. And let's take a look at how we can do this actually. So this is just copied from the previous slide. Well, just to remind you, we approximate f prime at xi with our finite difference formula d, so this is a function of h, and here I write it explicitly, plus this is the truncation error ch plus something of order h squared. Let's do the same, not for h, but for a spacing of 2h. And then we see, well, we just plug in 2h into this d function. What this basically comes down to is that we now evaluate f at xi plus 2, as indicated over here. Subtract f of xi and divide by the spacing here, which is xi plus 2 minus xi is 2h. Key to this observation is that, well, we should, in theory, approximate the same numerical value of the derivative here. And so by plugging in 2h, well, here we have d evaluated at 2h. We have here, well, we go c times h becomes 2 times c times h. We have doubled this spacing, so also this leading order term is doubled. The then term of order h squared, well, that is still of order h squared. It will be a bit bigger, but it's still of order h squared. And we make abstraction of how big it is exactly. It's of order h squared. Okay, so now let's try to see whether we can get rid of these error terms of order h. So this is an error term of order h, and this is also an error term of order h. Well, we can do this by combining formulas 1 and 2 in the following way. So if we take twice the first line and subtract from that the second line, we come up with the following. So we have here that the derivative of f at xi, well, simply just plugging in the right-hand sides here, we have 2 times this, so that's 2 times dh plus 2ch minus d2h. And we see that this 2ch will cancel out the other term over there. So by taking twice this minus this h order term cancels out. And what is left is only an error term of order h squared. So you see now that if we consider this new formula, this is then a new finite difference formula, and we can call it QH with order 2, because we see that this error term is of order h squared. So it's proportional to h squared, so it is of order 2. So this allows us to, with some very simple algebraic manipulation, we came up with a new formula QH, which is 2 times dH minus D evaluated at 2H, and that has an error of order 2. Now, if we plug in these, if we try to explicitly evaluate what this means in terms of function values, we can simply plug in these guys in here, and we see that this would be actually equivalent to the following finite difference formula over here. Now, if we take a brief step back and look at one of these overview slides from one of the previous sections, well, we see that this formula QH, which we derived in the previous section, in the previous slide, using Richardson extrapolation, that it could have also been derived from a Taylor series approach. So this is a 3-point forward difference scheme derived from a Taylor series approach. It's also derived explicitly in your textbook if you're interested. And it's exactly the same finite difference scheme that pops out. However, it's important to state that the way we derived this scheme didn't need any complicated Taylor series analysis or so. No, it was from a simple algebraic manipulation of two evaluations of a low order scheme D at two levels of grid refinement, let's say H. So we don't need to explicitly formulate or program this function Q. We can simply build it from D, which we already had. So we already started from this forward finite difference scheme. So let's put this Richardson extrapolation to the test in a practical example. And let's start out by first coding up the basic low accuracy scheme, this forward finite difference scheme, by making it into a function. So I will create a new function. I will call it, as we did in the previous slides, the function is called D, and the inputs are, well, a arbitrary function f, the point where we want to compute the derivative xi, and the offset, or let's say the spacing h, that we want to use in order to compute our finite difference formula. The output will be the finite difference approximation of the derivative df dx. And what we do here is, well, simply the body of this function will be that the finite difference approximation will be f evaluated at xi plus h minus f evaluated at xi divided by h. And that's simply a forward finite difference approximation of the derivative at the point xi. So let's save this function d that I save right now. And now let's put it to the test in a practical example. So I'll write this up in a script. Let's define first a function, and let's take a function that's very easy to differentiate analytically, and that is the exponential function, which we can define in the following way. And we want to compute the derivative at xi is equal to 1. And let's start with a spacing of h is 0.1. So we compute the finite difference derivative. We compute the error and then give this as an output. Or actually, let's compute the derivative at xi is equal to 0, because we know the derivative of an exponential function is that exponential function. So we know that the df dx true is simply the exponential function at x is equal to 0, which is equal to 1. Okay, now let's compute the finite difference derivative by calling this d function with the following arguments. And this will give us the finite difference approximation of the derivative. And then let's compute the error as the absolute difference of df dx true and df dx. And we can output it to the command window. So let's run the script. I first have to name it. Let's just call this Richardson demo. And we see that the error for these parameters is equal to 0.0517. Let's see whether we can get this error to be smaller. So let's divide h by 2. So we go from h is 0.1 to 0.05. And we see that, well, since this is a first order accurate scheme, that the error is also approximately halved. So instead of an error of 0.05, now we have an error of 0.025, which is consistent with the first order forward finite difference scheme. However, let's also apply a higher order accurate scheme. So we derived a more accurate scheme using Richardson extrapolation in the previous slides. So let's call this guy dfdx Richardson. And well, we saw that we can get a more accurate scheme by combining two of these first order accurate schemes D in the following way. So we just have twice the original scheme evaluated at a grid spacing h, and we subtract the same scheme but with a grid spacing of 2 times h. And let's also then compute the Richardson's error as this, and also we output it to the command window. So let me clear the output for a second, and let's see what happens now if we run this script. So the first observation is that, well, immediately the error of this Richardson extrapolated scheme is a lot lower than the original error of our first order forward finite difference scheme. Let's take a look at what happens if we now have this grid spacing h. Well, then we clearly see that although for the initial scheme we had a halving of the error consistent with a first order approximation of this derivative, for the Richardson extrapolation we see that by halving h we reduce the error with a factor 4, so consistent with a second order accurate finite difference scheme. So this is a practical application of how we could use these first order approximative schemes D to construct a higher order scheme using Richardson extrapolation.
Now, Richardson's extrapolation is not limited only to forward finite differences, but it can be applied to basically any finite difference scheme that you can think of. So let's take a look at if we can come up with a more accurate finite difference scheme, starting out from a central finite difference scheme, which is already second order as it is. So we start out from this scheme over here. Well, again, what we do is, well, we say that this is our finite difference function d, which is a function of h, and we expand our truncation error as a constant times this leading order power of h, so a constant times h squared, plus something of order h cubed. So that's our first step. Then in the second step, well, what we do is we evaluate this same right-hand side now not at a spacing of h, but we use 2h instead. So we replace h with 2h, both in this finite difference function, but also in the error terms. And we end up with here, if we plug in 2h instead of h, well, we get out 2 squared, which is 4 times c times h squared. The higher order terms, well, we're just going to keep them grouped under this order of h3. And then again, by combining these two equations, we can try to get rid of the second order error terms. So these leading order error terms of second order. And we can do this, for instance, by taking 4 times the first equation and subtracting the second equation. So this becomes 4ch squared minus 4ch squared gets canceled out. And what remains is that we have here 3f prime is equal to this thing on the right. We simply divide both sides by 3 and we end up with the following. So what we now have is we have our new finite difference formula, and let's call this again similar to the previous case. We can call this q of h, and we have then here a
truncation error, which is of order 3. So also with relative ease, we started here from a second order accurate scheme, so second order accurate, and using some simple manipulations, we were able to come up with a third order accurate numerical scheme. So wrapping up on Richardson extrapolation, the general strategy is to compute your lower order scheme D at 2 refinement levels. And we say that this lower order scheme is of order P, and we have seen examples in this lecture of P is equal to 1, for instance, a forward difference scheme, or in the previous slide, P is equal to 2, a central difference scheme. And you can simply then write out your approximation of the derivative as follows. We have the finite difference approximation. We have here the leading term of the truncation error, and then other terms of order h to the power p plus 1, so order p plus 1. We again evaluate our numerical approximation on the right-hand side at 2h. Outcomes here a leading order error term of 2 to the power p times c times h to the power p, and then using some algebraic manipulation of both equation 1 and 2, you can come up here with this general formula for any order p. So using a scheme of order p, by evaluating it twice and combining those two formulas, we are able to come up with a new scheme of order. So this is the new scheme that I wrote this line under now, and a error which is of order p plus 1. So this results in a new approximation scheme of order p plus 1. And then a final remark to make here is actually, I've been talking a lot about these truncation errors, about trying to obtain schemes of a higher order accuracy. But a valid remark that you might make at this point is, why even bother? Why not simply reduce the error that we're seeing by making h arbitrarily small? And that's true. If all the formulas and all the errors we've seen so far can be made arbitrarily small by making h arbitrarily small. So you could say I can just pick a smaller h. It won't cost me anything, but I can reduce the error up into an acceptable level, well, that I deem as acceptable. Now, in the final section of the chapter on numerical differentiation, I will show you that this is not really the case, and that there's kind of a catch which is important to keep in the back of your mind, and that reducing h does not always reduce the total error that you have in your approximation of the derivative.